In this video, we'll be talking about the Burrell distribution, which is very closely related to the Poisson distribution, and because of that, I've given it the same parameter lambda, which will play a very similar role to the Poisson lambda we were talking about before. So we're going to kind of lay the groundwork for this first, and then we'll do all the math for it. So the Borel distribution is best understood by thinking about a family tree. So let's say we have one individual right here represented by this green dot, and this is generation 0. So generation 0 always just has this one individual. Now this individual will have a certain number of children, and they will have children and so on. And the number of children they have is distributed as Poisson lambda, with the lambda being the same as the one we have in the Borel distribution here. So one thing we should note, though, that's special about the Borel distribution is that lambda can't just be any real number. It needs to lie in a certain range. So lambda, in this Borel distribution case, needs to be between 0 and 1 inclusive. So we say that the number of children they have, each individual has in any part of the tree, but let's talk about the first guy first, is distributed. So let's say G1 is distributed Poisson lambda, and I've named it G1 for generation 1 because the number of children this person have will dictate how many people are in generation 1 because they're just made up of all the descendants of this person. So because lambda is between 0 and 1 in this special case of the Borel distribution, we have an extinction property, which means that eventually this whole lineage must go extinct. And to kind of get an intuitive idea of that, think about why that's true. Each individual is giving birth to, on average, remember the mean of the Poisson is just the parameter, which is between 0 and 1. They're giving to birth, on average, less than one individual. So if that's true, if each individual is giving birth to, on average, less than 1, then eventually this lineage should go extinct. In a different case, let's say lambda was 2, each individual is, on average, giving birth to 2 people, then it's unclear what's happening. Surely it's growing because this person might give birth to 2, they might give birth to 2, and so on. It's just growing, and it's less clear. But in this case, it's pretty clear that it's going to eventually go extinct. So let's just do kind of a simulation, and let's be optimistic at first and do a few trials. Let's say this person gives birth to, let's say 2 people, okay? So one person here, one person here. So this is called generation 1. It's made up of these 2 individuals, and in this case, G1 would be 2, okay? Now let's say each of these individuals, let's say each of them gives, this person, let's say, gives birth to 1, 2, and let's say this person gives birth to 1. So this is generation 2 made up of these 3 individuals right here. Now notice that we're being very optimistic because lambda is between 0 and 1, yet I've given this person has 2 descendants, this person has 2 descendants, when really that's kind of unrealistic, kind of rare given our lambda right here. So now let's just keep going a few generations further. Let's say what happens is that this person now gives birth to, or has 1 descendant, this person has, let's say, 1 descendant, and let's say this person has no descendants, which is totally possible. So in generation 3, we have reduced it from 3 individuals to 2 individuals. Now let's go to generation 4. Let's say in generation 4 what happens is that this person has 1 descendant and this person has no descendants. So here we are in generation 4 with 1 individual left. Now we ask ourselves, how many people will be in generation 5? Well, let's say this person, which is the last individual in generation 4, gives birth to nobody. So that means there really is no generation 5. The cutoff is here. There was 4 generations. Really there's 5 if you count 0. So we'll say 0, 1, 2, 3, 4 generations of people. And now where does this x come in? X is going to be defined as the number of individuals in this family tree. So in this case, x is what? It's 1, 2, 3, 4, 5, 6, 7, 8, 9 individuals. So here x is equal to 9. And it turns out that there's the math behind it to derive the PMF of the Borel distribution involves queuing theory and a lot of waiting time calculations, which we haven't covered yet, and we may make videos on that in the future, but for now let's just take it as given and let's write it down. So we say that the probability, this is the PMF here, that x is equal to some value n is equal to, and of course we'll have to have some conditions here, it's e to the minus lambda n to the n minus 1, all that over n factorial in a certain case, and 0 otherwise. And what is a certain case? Well, we just kind of have to think about what values can n take. Surely it can't be negative, because you can't have a negative number of people in this family tree. Also, it can't be 0, because you always have at least 1 person, this founder or this initial person right here. So it needs to be 1, 2, 3, so on, all these integers like that. Okay, so this is our PMF, and I'll label it as such. So here's our given PMF. And what we're going to do now, we're going to intuitively give a good idea of what the mean is going to be, and then I'll tell you the variance, because the calculations would involve a little bit stuff that's beyond what we have covered so far. And then after that, we'll talk about a few interesting things about the Poisson distribution. So let's finish the Borel distribution first. So we want to find the expected value of x, right? What does that mean? We want to find the expected number of people who are in this entire family tree. That might seem difficult at first because there's so many different ways to get this 9, for example. Because this is one way to get the 9. Another way to get 9 people would be if we had this initial founder and he gave birth. He had all these 9 individuals just right out the front, and none of them had anyone. So there was just one. There's 2 generations, generation 0 and generation 1, which had 9 people. Also, a different extreme when we have 9 people is if this guy had 1 descendant, and that guy had 1 descendant, this guy had 1 descendant, so we just have this single chain going down and each generation had only 1 person in it. Okay? So because that might seem complicated how we're going to do this, but we're going to do it using kind of the Bernoulli binomial trick, where we express this x as the sum of something. And the most natural thing to do is express it as the sum of generations. So we're going to say x is going to be defined as g1 plus g2 plus g3 plus so on. And actually, let me squeeze something in here. I'm going to put 1 in the beginning plus all these g's. And these g's are going to be the number of people in each generation. So g1 is the number of people in generation 1, g2 is the number of people in generation 2, and so on. And I'm putting this 1 here because we always have that one guy in generation 0. So I could write g0, but since it's always 1, I will just write 1. So this is true because the number of people in this family tree is the sum of the number of people in each generation. Surely that's true. So really, if we want the expected value of x, we want the expected value of this large thing right here. So we can break it as the expected value of a sum is a sum of the expected values. So we have expected value of 1 is 1, plus expected value of generation 1, plus expected value generation 2, plus so on. Now, how are we going to do this? Now, expected people in generation 1 is what? Generation 1 always comes from this initial founder. Therefore, the expected number of people is just the expected number of people this founder creates. And since it's Poisson lambda, that's just lambda. So here we have just lambda. Now things get a little bit trickier, so we're going to have to think a little bit harder. Expected people in generation 2. Well, see, the problem is that there's not a guaranteed number of people in generation 1. Here there were 2. There could have easily just been 1. Maybe there's 0. We don't really know. So the expected number of people in generation 2 depends on the people in generation 1. Therefore, we're going to use the law of iterated expectations, which is going to be very helpful for us in this case. So if you need to go back, review it. But in a compact form, the law of iterated expectation says that expected value of some random variable, here we want g2, is equal to the expected value of the expected value of that random variable conditioned on some other random variable. In this case, we're going to use g1. So this inside part is saying what? It's saying that what is the expected number of people in generation 2 given that we have g1 people in generation 1. Okay? So if we know there's g1 people in generation 1, then that means each of them on average produces lambda people. So we're going to have lambda g1 people. So this guy right here, the inside expectation is just lambda g1, okay? And then we're taking the expectation of this. We want the expectation of lambda g1, which is just going to be, this lambda can come out since it's a constant, so we'll have lambda expected value g1. And that we know, right? We just said that was lambda. So it's lambda 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 squared. So this comes out as lambda squared. Similarly, if we just go on, we say expected value of g3, that's lambda cubed, and go on like that just till infinity. So what we have is a nice geometric series. We have 1 plus lambda squared, and so on. And the nice thing is that because of the bounds on lambda, now we need to be a little bit careful because I've included 1 here, but really, if you want this geometric series to converge, you should not include 1. So we want, under the assumption that lambda is less than 1, bigger than or equal to 0. It can be 0, because if it's 0, then it's just, the expected value just becomes 1, which does converge. Just 1. So as long as we're in this range right here, we can go ahead and write the sum of the geometric series formula. Remember, the formula sum is the first term over 1 minus the common ratio. So the first term here we have 1 over 1 minus the common ratio is lambda. Okay? So it's 1 over 1 minus lambda, and that is the expected value of x. Okay? So that's kind of an intuitive way of how to find it. So the next thing we want to do is say the variance of the Borel distribution, and the variance, the calculation is a little bit involved. It involves queuing theory and waiting times and stuff like that, stuff we haven't talked about yet. We may talk about it in the future, but for now let's just take it as given. So the variance of x is given by lambda over 1 minus lambda cubed. Okay, so here's the variance. And before we depart from the Borel distribution, let's just talk about a few interesting properties maybe of the expected value. So going back to our expected value, we see that the expected value depends only on this parameter lambda. So if this parameter lambda is as small as we can possibly make it, so let's say it's actually not 0, but very, very, very close to 0, then 1 minus lambda will be very, very close to 1, and 1 over that will be very, very close to 1, which makes sense, because if each individual is on average producing very close to 0 individuals, then on average we should have very close to 1 individuals in this entire tree, namely just this initial founder. Now, taking the opposite extreme, if we have lambda very, very close to 1, 0.999 something, then 1 minus that is very, very small, very close to 0, and 1 over that very small thing is huge. Does that make sense? Well, we're saying on average, there's very close to 1 individual. So we're saying it's pretty sure that each individual is producing 1 individual. So it'll be much harder for the lineage to go extinct, and it'll take many more individuals in this tree. So X will be a lot bigger. Okay, that makes sense. So now we will depart the Burrell distribution. It's a very interesting thing to think about. But let's talk about an interesting property of the Poisson distribution. So going back there. So let's take a little experiment. We're going to use the cars example again. So just for viewers who haven't seen the Poisson video, we have a city, and it's a city with many, many cars. You can say infinitely many cars, except the thing is that a certain proportion of them are red and the rest are white. So we're going to say P is the red proportion, therefore 1 minus P is the white proportion. Okay, so this is our basic setup, and what we're going to do, we're going to run a little experiment. We're going to pick a number, n, and how are we going to pick it? It's going to be distributed Poisson with parameter lambda. So basically we're going to take a Poisson distribution and choose a number in there, and that n will represent that number. Now what we're going to do, we're going to walk into the population of cars, of red and white cars, and we're going to put a blindfold on maybe, and just randomly select n cars, where n is given by this Poisson distribution, okay? And so we're just going to select those n cars, and of course we're going to have some red cars, some white cars, and what we want to know is the number of red cars we have selected independent of the number of white cars that we have selected? Intuitively it seems no, of course not, because if we have the number of red cars we selected is, let's say, x, let's let x be the number of red cars, then it must be that we have n minus x white cars, right? So n minus x is the number of white cars. And while this is true, we're going to see something weird, something unintuitive, that how the math works out in this guy is that the number of red cars is actually independent of the number of white cars in this case, where n, the number of total cars, is distributed Poisson lambda. So I know you don't believe me right now, so we're going to go ahead and do the math behind it. So let's first represent x as something a little bit cleaner to work with. So what is the number of red cars we pick out of these n? So it's as if we're going through the whole population and we're picking one car, picking another car, and then doing that n times. So x is going to be, let's say, equal to x1 plus x2 plus dot 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 plus xn, where these xi, so this is just a representative of these x subscripts, is distributed as Bernoulli P. So this is where all these things are coming together. We have a Bernoulli, here's a Poisson. So why is this making sense? This is because it's as if when you're picking a car, you're figuring out whether or not this is a red car. So if x1 is 1, then you did pick a red car. If x1 is 0, then you picked a white car. And this makes sense because this is Bernoulli with parameter p. So the probability that x is 1, that x1 is 1 is p, and the probability that x1 is 0 is 1 minus p, which exactly correlates with the proportion of red and white cars. Furthermore, I should say that all these xi's are independent of each other, because the fact that x1 was equal to 1 doesn't make any promises about what your next car you're going to pick is going to be, right? But the fact is that after you do this for all these n cars, remember, so we're going to let xi are measuring the success of choosing a red car. The sum of all these guys is going to be the number of red cars you select, correct? Because it's only going to be a 1 if you selected a red car. So x is going to be the number of red cars you select. So now this makes our job a little bit easier. because it allows us to think about this in a binomial sense. So to show you that these guys are actually independent, that this guy and this guy are actually independent, we're gonna find the joint probability law and show that it's actually the multiplication of the two individual probability laws, because that's a way to show independence. So we want to find probability that that x is equal to a and n minus x is equal to b. So that is the number of red cars is A and the number of white cars is B. So we're going to write this in a different way. This is exactly equivalent to saying that the number of cars total that we selected has to be A plus B, and of those, A were red, right? Because if A cars were red and B cars were white, then total there has to be that we had chosen A plus B cars, and A of them were red, okay? So this is the same exact probability, and now this will be a little bit easier to calculate. So first, what is the probability that this n was a plus b? Well, n was chosen to distribute Poisson lambda. So this is just simply plugging a plus b into the PMF for Poisson lambda. So we get e to the minus lambda, lambda to the a plus b over a plus b factorial. And now we have that a of those were red. So now remember, x is the sum of these Bernoulli guys. So it's actually binomial. It's because the sum of independent Bernoullis is binomial. So if x is binomial, and the total number we're choosing from is a plus b, and we need to choose a. So this is just using the binomial PMF. So we have a plus b choose a, p to the power of a, 1 minus p to the power of b. Okay, so this is our kind of nasty looking formula, but it's going to simplify very nicely. So on the back here, I'm going to copy it down. So we have e to the minus lambda. I'm going to break this lambda a and lambda power of b. So we have e to the minus lambda, lambda a, lambda b over a plus b factorial. And then I'm going to take this binomial coefficient and break it up into what it really is. So it's going to be a plus b factorial over a factorial b factorial, and what's remaining is p to the a, 1 minus p to the b. So we have p to the a, 1 minus p to the b. So here we have a nice cancellation right here, and let's see what else we can do about this. So let's write this e to the negative lambda in a different way. We're going to write it as e to the minus lambda, e to the minus e to the minus lambda p, e to the minus lambda, 1 minus p. Confirm this is correct, because if we add up the exponents, we get minus lambda p, minus lambda, plus lambda p. So this will go away, and we just have negative lambda. So this is actually e to the negative lambda, just written in a different way. Now we have p to the a, 1 minus p to the b, all that over a factorial b factorial. Now let's split this up into parts that go together. So this splitting up the parts, we're going to get e to the minus lambda p. We're going to get lambda. Oh, actually, I forgot to bring this lambda a, lambda b down. Let me put those here. Lambda a, lambda b. So this lambda a and this p a will combine to make lambda p a all over a factorial. That's one part. The other part is e to the minus lambda 1 minus p. And then this 1 minus p to the b and this lambda to the b will come together to make lambda 1 minus p to the b, all that over b factorial. Now notice something really, really interesting. These are just the PMFs for what? This is the PMF for a Poisson lambda p random variable, and likewise this is the PMF for a Poisson lambda 1 minus p random variable, right? Because what would this be? This would be e to the negative lambda p right there, lambda p to the power of a right there over a factorial, and likewise this has the same form. So this is just the PMF of a Poisson lambda p distribution evaluated at a, and this is the PMF of a Poisson lambda 1 minus p distribution evaluated at b. So if what we have really is the probability, so if we just for now call this, we're going to just name this for now x prime is going to be distributed that, and then y prime will be distributed like that. This is the probability that x prime equals a times the probability that y prime equals b. So notice we so far haven't said anything about this is just x prime and y prime, which are new random variables we created. This has nothing really about x and n minus x, which is really what we're interested in. So now we need to do a little sidetrack in thinking about what is the probability that x is equal to a. Okay, how is that distributed? Well, this really depends on what n is. So we need to do a little bit of a, we need to do this conditionally. So this is probability that x is equal to a, given n is equal to n, times the probability that n is equal to n, taken over all values n can possibly be is 1, actually 0, till infinity. Okay, so this is just using the condition. So we're going to have probability that x is equal to a given n is equal to n, probability n is equal to n. This part altogether is just the probability that x is equal to a and n is equal to n, summed over all values of n. So this will give us this exactly. Now, how do we do this? This is easy. This is just Poisson. So this is just e to the negative lambda, lambda to the n over n factorial. This guy is also pretty easy. So given that n is equal to n, this just becomes binomial, right? So this is just out of those n, choose a. P to the power of a, 1 minus p to the power of n minus a. So we need to multiply these and kind of simplify this a little bit. So we'll do exactly that. So let me rewrite that a little bit. So we have e to the minus lambda, lambda to the n over n factorial. I'll expand the binomial coefficient. We'll get it like this. So we see a nice cancellation already right there. And we want the sum of all these guys from n equals 0 till infinity. Since this is a sum over n, we can kind of pull out stuff that has nothing to do with n, such as this e to the negative lambda. So e to the negative lambda comes out. Let's go ahead and pull out n. We'll pull out a factorial. We'll go ahead and take out, let's see, we can take out p to the power of a. And that's about all we can take out. So this is n equals 0 to infinity. We're going to have e to the, we're going to have lambda to the n. We're going to have 1 minus p to the n minus a over n minus a factorial. Now what we need to do, actually, let me make a quick note. When we took the sum over n equals 0 to infinity, actually we need to take the sum as n goes from a to infinity, because if n is anything less than a, then something less than a, choose a is 0. So these are all zeros. So we can take the sum from n equals a till infinity. So let me just change that and change 0 to an a, just like that. And then we want the sum there. So then everything is in terms of n minus a, except this n does not have a negative a, but that's very easy to do. All we have to do is bring that outside. So we're going to have lambda to the power of a outside. We're going to take the sum n equals a till infinity, lambda to the n minus a. So all I did was I put n minus a here, and I put that lambda to the a here, so together they still make lambda to the n. And then we have 1 minus p to the n minus a, all over n minus a factorial. Okay, so now all we have to do is combine this, so we have e to the minus lambda, lambda to the a, p to the a, over a factorial, sum n equals a till infinity, lambda, 1 minus p, all together, putting that together, n minus a over n minus a factorial. We have a familiar. Since we're starting at a, this is an offset, because putting a in here we get 0, putting a here we get 0. So this is really the expansion, the power expansion for e to the power of this. So this is really e to the minus lambda, lambda to the a, p to the a, over a factorial, e to the inside thing here. So it's e to the lambda, 1 minus p. So let's see, we can simplify things a little bit. So we have equals lambda to the a, p to the a, e to the negative lambda, and we have a lambda here. So it's lambda 1 minus p minus 1. So it's just minus p all over a factorial. So let me bring that up a little bit. How does that look? So this lambda to the a, p to the a, I'll combine as lambda p to the a. And we have an e to the negative lambda p all over a factorial. And this is the distribution of a Poisson lambda p, right? Because the distribution of the Poisson lambda p would be e to the negative lambda p to the power of a factorial over a factorial. So this is, we find that x is distributed as Poisson lambda p, and here it's just evaluated at a. So going back to our previous paper, we see that x prime is really x, because they have the same distribution here, so we don't even need this prime. So this is really probability that x is equal to a, and we can do all these similar calculations that we just did right here for y, or n minus x, right here. And we'll see that y prime is really y, because they're distributed the same, so this is times probability that y equals b. So let me recap really quickly what's been going on here. So we said that we picked some number n, and we picked it as a Poisson distribution, distributed as Poisson lambda. And given that number n, we went to the population of cars, and we just randomly picked n cars without paying any attention to the color at all. And we found x, we picked x red cars, and n minus x white cars. So we would think the distribution, the probability x and n minus x would be independent, because given x, we know what n minus x is. And usually, yes, that's true, but the nuance here is that n is distributed Poisson lambda, and this Poisson distribution has these interesting properties like that. So to prove that they're independent, we showed that the probability that the number of red cars is A and the number of white cars is B is equal to the probability that the number of red cars is A times the probability the number of white cars is equal to B. So this is exactly how you show two random variables are independent. Okay, so this is very interesting. It didn't make much sense to me at first, but mathematically it's all here.